This is the design of reinforced concrete. The design data: span of girder L is equal to 40 meters, MDL 3720.98 kilonewton meter, FC prime 35 megapascal, FCI prime 28 megapascal, FPU 1860 megapascal, FPY 1676 megapascal. R is 0.85, assuming 50% time-dependent losses. MU is equal to the 1.25776.5 plus 1.63720.98 is equal to 12,885.368 kilonewton meter. Compute for effective width of flange, which is B. B is less than or equal to 40,000 over 4 is equal to 10,000 millimeter. B is less than or equal to 16 HF plus W, which is 16 times 750 plus 500 equal to 12,500. B is less than or equal to LC plus BW. LC is equal to 25 minus 500, that is 2,000. So B is 2,000 plus 500 is equal to 2,500. And we can use B as 2,500 because it is the least. Then check if A is greater than HF. Assume A is equal to 150 millimeter and phi is equal to 0.9. Summation of forces horizontal is equal to 0. Then 0.85 FC plus AB is equal to AS times FY. 0.85 times 35 times 150 times 25 is equal to AS times 415. AS is equal to 26,882.53 millimeters squared. Then compute the MU1, which is 0.9 AS times FY, quantity D minus A over 2. MU1 is equal to 0.9 26,822 plus 53 times 415, quantity 1352 minus 150 over 2 is equal to 12,550.78 kilonewton meter. Since MU1 is less than MU, design as T-beam. Next is determine AS. MU2, which is 0.9 times 0.85 FC prime times AB times D minus T over 2. MU2 is equal to 0.9 times 0.85 times 35 times 25 times 750 times 1325 minus 750 over 2. MU2 is equal to 47692.97 kilonewton meter. Since MU2 is greater than MU, A is less than T. Then we solve for A. Substituting the value of mu, we can get the value of A. The next is summation of forces horizontal. T is equal to C. 0.85 times FC prime AB equal to AS times FS, which is 0.85 times 35 times 154.2617 times 25 equal to AS times 415. The next is check if P minimum is less than P and P is less than P max. P max is equal to 0.016. P minimum is 1.4 over Fy, which is 1.4 over 415 is equal to 0.00337. P is AS over BD, which is 27646.3 over 25 times 1325 is equal to 0.0083. Use the value of P is equal to 0.0083. Design details: 28 pieces of 36 mm diameter or 35 pieces of 32 mm diameter. Computing for SC, which is 500 minus 36 times 7 minus 50 times 2 over 6 is equal to 25 mm. Check adequacy of T-beam. AS is 28 pieces of 36 diameter. Area of flange 25 times 750 is equal to 1875000 millimeter squared. T is equal to C. AS times Fy is equal to 0.85 FC prime times AC. Then we will get the value of AC. Since AC is less than area of flange, T is greater than A. And compute for A and C. AC is equal to 2/5 of A. So the value of A is 159.028 mm. And C is equal to 159.028 over 0.8. And C is equal to 198.785. Then check if C over dt and compute for mu3. C over dt is equal to 198.78.5 over 1325 is equal to 0.05, which is less than to 0.375. So we will use as the phi is 0.9. Computing mu3 is 0.9 times 0.85 times 35 times 159.028 times 25 times 1325 minus 159.028 over 2. Then the answer is 13258.12 kilonewton meter. Since mu3 is greater than mu, the design section is adequate. Design of prestressed concrete. This is the design data. Span of girder or L is 40 meters. MDL is 5776.6 kilonewton meter. ML is 3720.98 kilonewton meter. FC prime is 35 megapascal. FCI prime is 28 megapascal. FPU is 1860 megapascal. FPY is 1676 megapascal. And R is 0.85, assuming 15% time-dependent losses. Designing a symmetrical section using the following proportion. BW is 0.5 of B and HF is 0.25 of H. H is twice the B. Since the beam is post-tension, the tendon will have a variable eccentricity, which critical section at midspan. The allowable stresses in initial stage, FCI, which is negative 0.6 FCI prime, is equal to negative 16.8 MPa. Compression. The FTI is equal to 0.25 square root of 28 is equal to 1.32 MPa. That is tension. In the final stage, FCS is equal to negative 0.6 times 35 is equal to negative 21 MPa. Compression. FTS is 0.62 square root of 35 is equal to 3.67 MPa tension. Approximate self-weight of girder WO is equal to 0.2 quantity WD plus WL. ML is equal to 3720.98 kilonewton meter. Is equal to 1/8 WL 40 meters squared. WL is equal to 18.6 kilonewton meter. And MD is equal to 5776.5 equal to 1/8 WD 40 times 2. WD is equal to 28.8 kilonewton per meter. WO is equal to 0.2 quantity 18.6 plus 28.88. So it equals to 9.5 kilonewton per meter. MO is equal to 1/8 times 9.5 times 40 squared equal to 1900 kilonewton meter. First trial. Section needed to be adjusted. Required section moduli. The top fiber ST is greater than or equal to 1 minus R times MO plus MD plus ML over RFTI minus FCS. And substitute the value. We will get the value of 442.21 times 10 raised to 6 cubic millimeter. At the bottom fiber, SB is greater than or equal to 1 minus R times MO plus MD plus ML over FTS minus RFCI. Substitute again the value. Then we will get the value of 544.98 times 10 raised to 6 cubic millimeter. The bottom fiber governs because it's the larger value. The next is determine the dimensions. S is equal to I over C, where the symmetrical I section is C is equal to H over 2 and I is equal to 1 over 12 times B times height cube minus 1 over 12 times B minus BW times H minus 2HF cube. And substitute the value and given the proportion, we will get the value of 544.98 times 10 raised to 6 millimeter cube equal to 5 over 32 BH squared. If H is 2B, B is equal to 961.167 millimeter. Pwede mo siyang i-round up ng 1,000 millimeter. H is equal to 1992.335 millimeter. Pwede mo din siya i-round up ng 2,000 millimeter. Then let's try the value of B is equal to 1,000, HF is 500, H is 2,000, and BW is 500 mm, all in millimeters. Check the section modulus. S provided. 1 over 12 times 1,000 times 2,000 cube minus 1 over 12 times 500 times 1,000 cube over 1,000 is equal to 625 times 10 raised to 6 cubic millimeter. The actual WO is 23.6 kilonewton per meter. Quantity 1 times 2 minus 0.5 times 1 quantity is equal to 35.4 kilonewton per meter. MO is equal to 1 over 8, 35.4 times 40 squared is equal to 7,080 kilonewton meter. Adjusted, the S required, the SB, is 588.27 times 10 raised to 6 cubic millimeter. Since the section modulus provided is greater than the required, we can adapt the dimensions. Let's compute the centroid of the stress, which is FCCI. FCCI is FTI minus CT over H, FTI minus FCI. 1.32 minus 1,000 over 2,000 quantity, 1.32 minus 16.8 is equal to negative 7.74 MPa. The initial pre-stress force required, or PI, is negative 7.74 times 1,500,000 is equal to negative 11,610 times 10 raised to 3 Newton, which is compression. The eccentricity at midspan, E, is FTI minus FCCI times ST over P plus MO over PI. And the value is negative 1097.54 mm below the neutral axis. E is greater than H over 2, so not applicable. Adjust the section. The second trial section is adjusted for more economical design. E is greater than H over 2. It's not applicable and adjusted. Check the modulus. S provided is 2,109.375 times 10 raised to 6 millimeter cube. WO is 79.65 kN. MO is 15.93 times 10 raised to 3 kilonewton meter. The S required is 6.22.199 times 10 raised to 6 millimeter cube. And since the section modulus provided is greater than the required, we can adapt the dimension. Compute again the centroidal stress, which is negative 7.74 MPa. Initial pre-stress force required, or PI, is equal to negative 26.123 times 10 raised to 3 kilonewton compressive. Using grade 1860 megapascal for post-tension beam, FPI allowed is equal to 0.7 FPU, which is 0.71860 MPa. FPI allowed is equal to 1,302 MPa. The area of pre-stressing tendon required, or APS required, which is PI over FPI allowed, and equal to 26.123 times 10 raised to 6 over 1,302 is equal to 20.066 times 10 raised to 3 millimeters squared. The number of 15 mm diameter strand, N is equal to APS required over APS over strand. 20.066 times 10 raised to 3 over 140 is equal to 144 15 mm diameter strand, 10 tendon, 14 cables, 1 tendon, 4 cables. And check the strength capacity of the section. APS 144 15 mm diameter strand with E is equal to 1,341.383 mm. APS is 144 times 140 mm squared is equal to 20,160 mm squared. And DP is equal to 2,841.383 mm. And P, 0.8. BP is 0.00473. Use grouted stress relief tendon. FPI is 0.7 FPU, and since 0.7 FPU is greater than 0.5 FPU, thus code is applicable. And FPS is equal to 1,696.361 megapascal. Then check if if A is greater than HF. Yan. 0.85 times 35 times A times 1.5 equal to 20,160 times 1,696.361. A is equals to 766.356, which is greater than 750 mm. Thus, the analyzed as a flange section. Check RI. RI is equal to 0.00473 times 1,696.361 over 35 is equal to 0.229, and 0.36 times 8 is equal to 0.288, which is greater than the RI, thus the tension failure. Solve for MN. MN is 0.85 times 35 times 766.356 times 750 times 2,841.381 minus 766.356 over 2 plus 0.85 times 35 times 15 minus 750 times 750 times 2,841.383 minus 750 over 2. And MN is equal to 83.307 times 10 raised to 3 kilonewton meter. Check C over dt and solve for ultimate moment capacity. And C over dt is equals to 0.34, which is less than to 0.375. So, we can use the value of 0.9. The ultimate moment capacity is 0.9 times 83.307 times 10 raised to 3 kilonewton meter is equal to 74,976.3 kilonewton meter. Then, actual factor design moment, WU, is 1.2 times 79.65 plus 28.88 plus 1.6 times 18.6 is equal to 159.996 kilonewton per meter. MU is equal to 1 over 8, 159.96 times 40 squared is equal to 31,999.2 kilonewton meter. Since MU is less than the ultimate moment capacity, then the section is adequate. For the purpose of more economical design, adjust the section. In designing a structure, one must consider alternative materials to have choices in picking the most economical, effective, and strongest material. As an initial assessment of designing the bridge, it is said that the more advantageous materials will be the prestressed concrete, since the bridge is spanning over 9 meters, and by computing the moment capacity of reinforced and prestressed concrete.